Yeah, so what we've got coming up, right, is so we decided we are going to have our exam 2 kind of late on Tuesday the 16th, so next Tuesday, right?
Yeah.
5:30 to 8:30. I think I haven't reserved, but I think probably in this room here.
I doubt that.
Yeah, anybody has it at that time. We have the presentations that we talked about. Those will be on the last day, 19th, last day of class. And I think that's all we'll do that day probably, so we can get out early on the last day. Other things that we have is we have one more homework 6. And so I think I will essentially give that to you guys at the exam, and then we can run it until like the 24th. And then the final, I guess that doesn't really give me much time to, well, I could probably do it the next morning or something. So would be from the 25th through the 1st of May. So it's take home. And so what I ask on the take home, you can use any of the references and things like that, but don't, I guess I never really said this, but I think you guys have followed this, but don't go like searching the primary literature and things like this. Right.
What does it mean, primary literature?
Well, sometimes I might give you a data set or something that maybe is published somewhere.
Oh.
Right. So don't go searching for the papers.
Can you use the website, the NMR database?
Yeah.
Yeah,
There's
I think.
an update for that.
Oh.
Yeah, they changed it.
Yeah, the NMR.
Yeah.
Uh-huh.
Yeah.
Oh.
Really nice.
Oh, I'll have to look at that.
Fancy.
Yeah.
No, it's fancy.
Okay.
Yeah.
Yes, I think you can use that, but then you need to say how you used it.
Oh, for justification.
Yeah.
Mhm.
Right.
Yeah. If I was looking at primary literature for this, my grades would be significantly better.
Yeah, so don't spend the whole time just trying to find the paper so you can write the structure out.
Yeah.
Right. That it doesn't serve anything as far as learning here. Obviously in research, you would do that, but we're trying to learn how to interpret data. All right, so those are the things we've got coming up. Here we have it up here. We talked about all of the 2D NMR experiments, numerous experiments in each of these homonuclear and heteronuclear categories, and tried to do at least enough applications so you can see maybe how and where they would be applied or utilized. We spent just a little time last class talking about NMR of N15, F19, and P31. And so what we have left for this week, and I guess next Monday, is we're going to do some talking about stereochemistry.
Monday?
Oh, not Monday, Wednesday.
Okay.
Yeah, for some reason I thought we were meeting Monday and Wednesdays instead of Wednesday and Friday. Yeah, so Wednesday. I'm not sure how relevant some of this is for you guys, but, we'll kind of survey through, who knows, some different approaches, but it probably is more designed towards, well, like everything I've done, is more towards natural products or organic synthetic compounds or things like that. All right, so what we're going to do is we're going to start out talking about kind of types of stereochemistry, so relative versus absolute stereochemistries. And then we will talk first about relative stereochemistry, probably today, and then and then one of the next days we'll talk about some ways to approach absolute stereochemistry. Okay? Okay, so this is just a summary of what we got. So if we're going to talk about first, like I just said, absolute versus relative stereochemistries. To determine relative stereochemistries, we can use several methods. We can just look at proton-proton couplings. We can use NOE experiments. We can derivatize certain types of functional groups that may place the molecule in certain conformations, so then we can better utilize proton-proton couplings. And we can even use other kinds of couplings as well to determine stereochemistries, like proton C13 coupling constants. Determining absolute stereochemistry, we haven't really defined these yet, but we'll look at these different methods. Circular dichroism, so CD, an application of CD for certain functional groups, the exciton chirality method, and then Mosher's method is a way to determine the absolute stereochemistry of secondary alcohols using NMR, derivatizing it and then using NMR. And there's greater applications and methods that have developed from these, but these are a good starting point and serve as an example. All right, so relative versus absolute stereochemistry. So what's the difference?
It's a good question.
No idea.
Okay, so it's good that we're covering this then.
Yes.
Okay, so relative stereochemistry kind of involves what it says, relative. So it's if you have more than one chiral center or stereochemical unit, then we're talking about how one relates to the other. So we could use relative terms like cis or trans, things like this, all right? Or so like for a molecule that I've drawn here, we could have one structure where these two groups, the OH and the methyl group, are on the same side. So we could have it cis, or we could have it trans. Okay, so between cis and trans, this is relative stereochemistry. Okay, but if you look at those two compounds, are those the only two stereoisomers that are possible? No? What else could we do?
No, I lied. Oh, you could do
RS.
RS,
like
yeah.
Right. So we have another cis that we could draw, right? I just arbitrarily drew wedges for both of those bonds, so they're pointing up. But I could also point them both down. This is still cis, right? Because both groups are on the same side. Or likewise, I could do it down here. I could draw the OH being back and the methyl group being up. This is still trans. So the difference between these two is still relative stereochemistry. But what's the difference between these two?
Oh, dude. Those two trans or those two cis.
Right. Are they the same?
No.
No?
They're the same, I think.
Can you superimpose them? Can you take one and overlap them and have them be exactly the same?
No, so they're diastereomers. Did I say the wrong thing? I did say the wrong thing. Well, no, they should, right?
Well, so we have several options. Okay, options, they could be the same.
They're not.
They could be mirror images of one another. And what do we call molecules? So let me hear. What do we call? So if they're the same, here, let me do this slightly different. Okay, let's say they're going to be different. If they're different, they're going to be stereoisomers. Right? Because all of the bonds are connected to the same atoms, and they're different just because of the orientations of the bonds. If they're different, they could be mirror images. Or they could be not mirror images.
They
Huh?
are mirror images.
Those two are mirror images?
Yeah.
Yeah, so because we could take one of them, say the one on the right, we could flip it over like this, and they would just be, reflecting each other. Okay, so what do we call molecules that are different, but they're mirror images?
Enantiomers.
Enantiomers. Okay, and so the difference between the enantiomers is the absolute stereochemistry. Okay, so if we want to determine the absolute stereochemistry, we have to actually determine, for example, the R and the S of the chiral centers. Right? So if we wrote this, so if I did this, okay, this would be an R chiral center here. This one would be S. And so this one should be, if I did it right, this one should be S, and this R. Okay, so when we have enantiomers, because they're mirror images, every chiral center is opposite. Okay? If we did these down here, this one should still be R because it's the same as up above, but this should be R because we switched it. And over here, this should be S and S. Right, so again, these two are enantiomers. And the chiralities of each of the centers are opposite. But when we have relative stereochemistry going up and down here, right, we have a cis versus a trans, then notice that one of those chiral centers matches and the other one is different. Right? So this means they're stereoisomers, but they're not mirror images. Right? So I could fill this out down here. So if they're mirror images down here, they are enantiomers. And if they're not mirror images, then what do we call them? Diastereomers. Right, so these are diastereomers. Likewise here. Likewise, across like this. Okay, so relative stereochemistry just has to do with the relative orientations of different groups. Absolute stereochemistry has to do with the actual R and S of the individual groups. Okay? Because we can determine the relative stereochemistry and have a mixture, a racemic mixture. It would be a one-to-one mixture of enantiomers. Okay? So, I think oftentimes determining the relative stereochemistry is easier than the absolute. Because if we have mixtures, if we have enantiomers, they should, I guess you have to put a limitation. In an achiral environment, they should have exactly the same properties. Okay? If you put them in a chiral environment, say interacting with protein or
Light probably.
yeah, maybe that's what we'll do when we do it. Yeah, polarized light. If you actually could put them in, say, a chiral solvent or something like that, they should have different. If you crystallize them,
Yeah.
huh?
Yeah. If you crystallize them, they will be different.
Yeah.
There is three class
Yes.
topography.
Yep. Sometimes you'll crystallize something out and you only get one form of the.
Yeah, I think that's
hypothetically,
the
inorganic.
famous, lactose or something
Yeah.
was with
Mechanical
Pasteur or somebody like that who, crystallized out one and picked them apart one crystal at a time. Okay, so let's talk first about relative stereochemistry. So we know some methods to determine some relative stereochemistry already. Okay, so one of the common ways is to just look at the 3-bond proton-proton coupling constants, because we know that the size of the coupling constant depends upon the dihedral angle, right? And we looked at this before. So if we have free rotation, then the average is usually between 6 and 8 hertz between those. But if our molecule has restricted rotation, either hindered and it's favoring some conformations over others, or if it's, say, in a ring or something like that holds us in certain conformations, then there's a clear relationship to the dihedral angle. And we talked about this before. This is called the Karplus correlation. If we have dihedral angles that are
So based on the angle they have, the coupling constant goes down and goes up.
Mm-hmm. Right. So it's the biggest when
180 degrees.
180 when they're when they're anti to one another.
Okay. And they are gauge.
When they're gauche,
Gauche.
so that would be at like 60 degrees. Right? So at 60 degrees, it's going to be kind of small. Or at 120.
80.
Huh?
Why at 80 is the lowest?
Yeah, so 80, close to 90. I don't know why it's not right at 90.
Mm-hmm.
But what essentially happens is when they go to 90 degrees, there's very little orbital overlap because the orbitals are orthogonal to one another. And so there's very little interaction. So, I think these are the ranges that we see. The next highest, kind of a maximum over here is where the angle is 0 degrees, but those are eclipsed, and we don't really see that as much, right? Usually it's going to be somewhat off of that. But we can clearly have, large coupling constants versus, gauche, which would be either 60 or 120, and I don't know why this isn't exactly symmetrical. Because what's the difference between
This one and that one.
this one and this one, right? But so we can kind of break them into large versus small, right? Whether they're, diaxial or anti to one another, or gauche, which could be, if we look at a cyclohexane ring, they can be, so the diaxial, like this, can have large couplings between 6 and 14 hertz, whereas either the axial to equatorial, so we could have axial to equatorial, 0 to 5, or equatorial to equatorial is also 0 to 5. So essentially we have, large and small. So, I think in these, usually, well, if it's just cyclohexane itself, well, they're equivalent because it's the chair conformations are flipping and they're, equivalent, so there's no coupling. So in order to use these, there has to be some substituents that favor, one conformation over the other.
Because of the big bulky groups?
Yeah. Some kind of groups, because, right, if we have bigger groups, they're going to want to be equatorial rather than axial if possible. All right, so an example, this is a compound that we worked on in my group, and we had 2 ring systems here that we wanted to try to determine. And so this one down here, right, is essentially a 6-membered ring, right? Even though we have an sp2 hybridized carbon at 1, then, it should basically be in a chair, right? And then the other one is over here, right? And this is somewhat flattened, but we might have, be able to do some coupling constants on that side as well. All right, so what we did is we looked at the various coupling constants. And on the right side over here, what we found is that they were all, I guess, why did I put those all as A's? From here to here, and from here to here, these were all around 12 hertz. Okay, so suggesting that all 3 of those are axial, are all axial. Now, what we didn't get from this, though, is the stereochemistry.
So it's not 14, it's 12?
What?
Those 2 ones, those were axial.
Yes.
So why is that 14? Because we said the magnitude of the splitting based on appendix F, they should be from 6 to 14.
Right.
So why you're around 12? It's lower than 14.
Well, it's 6 to 14,
Oh,
so I think it's less common for them to be at 14, right?
Okay.
Yeah, so I think it depends on what groups are there, and and maybe this is flattened out a little bit because of the ketone, or yeah, I think there's various factors that are going to influence these a little bit. So the position that we couldn't get, though, in this is over here from the coupling constants, because that group is just isolated. There's no other protons that are, well, there's the methyl, but there's no proton on the ring that's coupling to that. So we'd have to use a different method to determine that center. Over here, these 2 protons had roughly a 3 to 4 hertz coupling. All right, and it's a 5-membered ring, so it may be it's on a 6-membered ring, I guess, but that has a sp2, a double bond over here, and then it has a 5-member ring, so it's a little more flattened out. But I think that we used this as one support that they would be on the same side like this. But then we have some other data to support that as well. Okay, so what's another way that we could work on the stereochemistry here out of NMR experiments that we've learned?
HMQC?
Well, will HMQC get us information about
No.
stereochemistry?
No. Well, I mean, it'll tell you the diastereotopic protons, but it doesn't give you
Right.
stereochemistry, yeah.
Did you get any information from the CNMR for stereochemistry or not?
Sometimes. Well, because sometimes if you know it's in a six-membered ring, the chemical shifts can change whether they're in groups are in equatorial or axial positions. So I think when they're axial, they're actually a little bit further upfield usually than they are when they're in equatorial. So that can help. But what's something else that we've learned?
Oh, NOE?
NOE, right? Because if we can observe through space interactions, that can tell us relative orientations as well. Okay, so on the right side of the structure here, right, we had already determined these three positions over here, but then we saw an NOE from this axial proton here to this proton that was isolated over here, so that fixed both of those as axial. All right, because we're not going to see axial to, we wouldn't see axial on one side to an equatorial position on the other side of the ring. Right, we talked about that these are good for these diaxial positions. On the other side, we did see an NOE between these two protons, which again confirms what we had from the coupling constants. But we also see an NOE from this proton here at 3 to this ethyl group on the other side, right? So it kind of puts those two groups on the same side. So usually what we're doing with NOE is we're trying to, position groups on the same side. And if we don't see something, then maybe they're on the opposite side. Though I think the thing to...
How do we measure the NOE here?
Well, we could either do, the one-dimensional ones that we learned about is the difference NOE, right, where we take a reference spectrum and then we irradiate one of the protons. Usually what we're doing is we're irradiating it during the pre-acquisition delay and then turning off that decoupling because we're not trying to decouple the spectrum. We just we turn we irradiate before the pulse, so we put energy into it and then we turn it off and we see where that energy propagates to. We can either do one-dimensional difference NOE, or we could do like a nosy or a rosy two-dimensional spectra, right? And in those cases, the NOEs are observed as, off-diagonal cross peaks, like in the COSY. Okay, so the challenging point here as well was then we have relative stereochemistries on this end and this end, but how do we connect one end to the other end? Well, Toxie's still just telling us through bond, right? Spin systems. Yeah. Okay, so we have relative over here.
Can we use relative for each of them to each other?
Well, not really. So one side could essentially be like RSS, and the other one could be, SR, but we don't know if one end is, flipped versus the other. Okay, so we'll get back to this one. Okay, and so how do we determine this part? Okay, so yeah, we'll come back to this one. All right, so here's some more examples of how NOE can be used. So if we can see these, I think, let's see, I think that in this case, they already knew this one. Chiral center there, and they were trying to determine stereochemistry of the other three chiral centers. Okay, so first off, so we're trying to relate everything to that, right? So they could see NOE over to here. They could see NOE over to here. Of course, it's just a CH2 group over here. But from that same proton, because the two protons here would be diastereotopic, right? So they see NOE from one of those over to here. So they get kind of this triangle that shows that those three groups are on the same side. Alternatively, they can look at this, and they don't see an NOE to this one here. So what I was going to say a moment ago, and I forgot, is that one thing you want to make sure if you're doing NOE is to focus on the observed NOEs, okay? And you don't want to, so you want to be careful drawing conclusions from the lack of NOEs. Okay, so don't make big conclusions from negative data. Okay, because sometimes you don't see it, right? Okay, so starting with this other proton over here then, they can see NOE to the adjacent group. So they hadn't seen from here to here, so they can see these two groups that are back behind. So these are on the same side. And then that one goes to the next one at the ring junction, and then to the other proton of that diastereotopic pair, right? So essentially they're seeing all the protons on one side and then all the protons on the other side. All right, so they can really fix those. All right, this other example, which I was looking at this morning too, which was, some of it's a little bit curious to me, but so here, what I guess they had these relative stereochemistries here, but they were trying to determine the stereochemistry at this methyl group. Okay, so what they say.
So they know the stereochemistry of the others and just...
I guess so, because those are all drawn with dashes and wedges already. And this one has the wiggly line, which means it's unknown or a mixture. So they say they see a NOE from this methyl group to the proton next to it. So this proton over here. And that's kind of all they see from that methyl group. But from the H, they see NOEs across the ring. So across here. Is that right? No, that's not right. Because that would be 1,4. That wouldn't work. Oops. from here. Right? So these 1-3 relationships, oops,
Is it one?
we would see those, huh?
Is it 4 bonds or?
Well, if you count the positions around here, 1, 2, 3, so it's a 1-3 diaxial arrangement here. So they can see them here, but they don't see it over here. But what was interesting to me here is that they have all these other substituents, an OH, and these are these tert-butyl dimethylsilyl, essentially protecting groups, and this one's axial and this one's axial, and the OH is axial. For these, I guess these other two over here being equatorial are the most important ones. So one thing you think about these protecting groups as being so big, right? So they should be, you'd think, they should be what controls whether it should be axial or equatorial, but by the time you go to an oxygen and out to a silicon, and that bond is longer than a carbon-oxygen bond because silicon is bigger, and then you have those groups, these big groups end up being farther away, and so they don't have as much of an impact. So I tried to think about what if we had the other stereochemistry at that position. I think if we had the other stereochemistry, we'd probably have the other chair conformations as well. So I think we would probably have, well, I don't know for sure if this group would go OTB, DMS, H. If this was then the opposite stereochemistry, and that would allow these other groups.
The methyl needs to be axial. If you're doing opposite stereochemistry, because right now it looks equatorial.
Well, it would be. I switched I flipped the chair.
Yeah. Well, in the first one, it's equatorial, but in the way that you've drawn it, with the flipped chair, that would still be equatorial.
Well, if this one was pointing down, and I just flipped this stereochemistry here, this one should be up. Right? If these two were on the same side, both equatorial, then now I have one axial and one equatorial. So I switched the stereochemistry here. But I also flipped the chair because I think if you flip that one, then possibly all of these other groups could be equatorial. Like this.
So the methyl group, even though it was equatorial in the first chair, when you flipped it, it still stayed equatorial.
Right, because if I kept everything the same, if I did the ring flip, then that methyl group would go from equatorial to axial. Right?
But if you're changing this,
But I changed the configuration of that position.
That's where I was.
Right. So I'm not just doing a ring flip. So here, so this is changed configuration. Right? And so if this was the case, and if it adopted this chair, then, you should see things like, over to here, right? And then across here, and then from these two over to there as well, right? Because those are axial positions. So, I guess you would see very different if it was, I'm assuming that if you switch that one position, you would adopt a chair that would just have a single group being axial now.
That makes sense. Okay.
So yeah, I just thought it was interesting that, all of these groups here and here, and OH isn't so big, but all of these are axial. But the 1-3 arrangements are pretty good for NOE. Okay? All right, so this is one approach. There are other approaches where you have something acyclic like this with these 1,3 diols. There's a way that you can derivatize them in order to make them into a 6-membered ring. And then the arrangements become fixed, and so then you could use the same techniques we've just talked about. So a common way to do this is that you take these, one or the other, and you essentially react them. You might use different conditions than this, but with acetone.
Do we observe any change in the stereochemistry after substitution in the reaction? Or it always goes the direction in the stereochemistry that it was before?
Could these stereochemistries here change during this reaction? No, not really, because the reaction's always here. Is between these alcohols and this ketone, right? So these positions won't change. Okay, but so what we could get then is what we call an acetonides. So it has this R1 and R2. Like this. And if we had this other ones, we could call this being anti and this being syn. Anti on the opposite side, syn being on the same side. Okay, we could get these two. Okay, so what we might be able to do is just look at, it's possible that we might be able to just look at the coupling constants around this part of the ring now, because we got a 6-membered ring, so it should adopt one would think, maybe a chair conformation or NOEs. But what we can actually do in this method is to just look at the C13 chemical shifts of these methyl groups and can allow us to determine the stereochemistry. Okay, so the way that this works, well, let's just look at, here's kind of the results, and then we'll talk about why. All right, so if we have the syn, if we started with the syn diol, where those two alcohols are both coming up, and we form these acetonides, and then we do the C13 NMR, and we just look at those two methyl groups. What we observe is that we get one of them roughly around 19 or 20 parts per million, and the other one up near 30 parts per million. Okay? And this other graph over here looks at the difference between their chemical shifts. So we see a difference in chemical shift of like 10 parts per million. Okay, so the chemical shifts for those two methyl groups are quite different from one another. If we have the anti-1,3-diol, and we do this, then what we see is that most of them have very similar chemical shifts. Okay, there's a little more variation here, but both methyl groups are around 24 or 25 parts per million. And if we look at this other graph for the difference, mostly the differences are quite small. All right, so why would this be? Right, this was the syn. They have very different chemical shifts because we have a clear axial and equatorial. And for the anti, we go to the twist boat, and they're in the similar environments, and so we just get roughly similar chemical shifts. Okay? So what we have to do to understand this is we have to look at the chair conformations. Okay? So if we start out, if we have the anti here, I'm going to just draw these. I use blue. Oxygen, oxygen. Like this. And here's our two methyl groups. And the other groups, one would be, here's R1. And over here, this would put R2 down here. Okay, so for anti, these two groups, one would be axial and one would be equatorial. Okay, let's just draw out the other one. Okay, and in this case, both R1 and R2 are equatorial. Okay, so part of the argument here is that if we have the anti and we have one of these groups axial and equatorial, then the molecule does not, in fact, stay in a chair. It kind of rotates over to more like a twist boat, which they draw like this. And this allows this R1 to be like that, and this R2 to be like this. Okay, so this is a twist boat. All right, and so this allows both of these substituents to rotate into more of a kind of pseudo-equatorial or equatorial type of position. And we avoid any strong steric interactions between this one R group and one of the methyl groups of the acetonide. Okay? So now, if we look at these two structures that we have, we've got the twist boat and we have the chair for the syn one, that these two have very different chemical shifts because one is clearly axial and one is equatorial. and usually the axial one is more upfield. So this one would be, I guess, around 20, and this one would be more like around 30. But in the twist boat, notice that these two methyl groups are in almost identical situations.
Because of a twist about over the oxygens?
Right. They both have the same groups that are nearby. They're both like this. They both have same relationship to the oxygens, and these alkyl groups here are both pointing away from these methyl groups too. Okay, so these are in quite similar environments. So they have similar chemical shifts. Okay, and so that's why for this sin, they've actually applied this. I didn't show a bunch of examples for this. Even with molecules with multiple, say there's classes of compounds that have just 1,3 diols, one after another, and they just will make these acetonides, and you may have, if you had something that was like, OH here, OH here, OH here, OH here, something like this, then you make these acetonides, and in some cases, you might get the acetonide here and here, right? And in another molecule, you might have to separate them. You might get the acetonide here, right? And so by comparing those two molecules, you could relate, this stereochemistry to this, to this, to this, on down the line.
That would be a fun column.
Yeah, right. Well, they're all just diastereomers, so maybe they separate all right. The other thing that you can actually do, if you have small amounts of material, and if you need to separate some and you have small amounts of material, if small amount of compound, you can use C13 labeled acetone, because really all you're looking for is the chemical shifts of the methyl groups, right? And so if you all the other carbon signals would be small, but if those of the methyl group stand out strong, that's all you really need to see. Okay? All right. So one more method we'll kind of briefly go through. I've never done this, and it's pretty complicated, but I guess just as a demonstration, we'll just see what they consider a little bit. So we've looked at, dihedral angles and coupling constants between, protons, but there's some methods that you can actually start to bring in proton-carbon coupling constants as well. And these are applied to some pretty complicated acyclic systems. And so, in general, we already have, this is what we've already talked about here, right? Is just the Karplus arrangement between the dihedral angles. But you can also do the similar things down here. So here's a 3-bond coupling as well, right? But it's not between protons, but it's 3-bond coupling constant between a carbon and a proton, right? So between like this, the methyl group or that carbon and this hydrogen.
So we have hydrogen carbon angle, something like that.
Right, it's still a dihedral angle, right? But we're just one end of the dihedral angle is carbon. Okay? And in these, all of these here, the ones that are in parentheses, the lower values, are for 1,2 dioxygenated.
So one side is oxygen instead of carbon, and the other one is hydrogen?
Well, I think, for example, like these other substituents, like you might have 2 oxygens on these other groups. Okay, like diols or methoxy and an OH or something like that. Just because when they were applying it, these were kind of some common. I'll show you an example in a minute of a compound that they worked on. So you can see that, they included those because they're common in natural products. Okay, so what we want to see here, though, is that for these 3-bond carbon-hydrogen couplings, we can have a 180-degree dihedral angle, and the coupling constant is between 6 and 8 hertz. But if those two are 60 degrees or gauche to one another, we have a 1 to 3 hertz coupling constant. Right? So it's actually not that much different, even though these are carbon-hydrogen coupling constants rather than the proton-proton coupling constants. But what we essentially see, again, is that if they are anti, we get what they categorize as a larger coupling constant, and if they're gauche, you get a smaller one. 1 to 3 hertz.
What about the first and the second for two bonds, carbon hydrogen?
Right, so we're getting there.
Okay.
So they can also use it for 2-bond couplings, and so that's going to be a coupling between this hydrogen here and this carbon right here. So the dihedral angle that they're looking at here that has an influence on the size of this coupling constant is the arrangement of this oxygen relative to where the hydrogen is. Okay, so it's not part of the coupling system, but apparently it influences the size of the coupling constant. Maybe because it can donate some electrons into the bond or something like that. And again, if the hydrogen is anti to that alcohol or to that oxygen, then, in this case, these are backwards. I didn't notice that. If those are anti, they get a small coupling constant, 0 to -2, and if they are gauche, they get it -5 to -7, so a larger coupling constant. Okay? So it's kind of reverse, but there is a relationship. Okay, so they're just trying to find these relationships between the conformation or the actual stereochemistry related to the sizes of the coupling constants. Okay? So here's some examples of how they do it too, is they mapped these possibilities all out. So in these two, they have these 2 chiral centers adjacent, so 1-2 arrangement. And they have 2 possibilities where those groups can either be here. They have this X group and this Y group. And if those X groups, or X and Y, are on the same side, so this is kind of like sin. They call this 3O. And then they look at essentially different conformations here and different arrangements of those groups relative to one another. So here's the X and the Y here. Here's X and Y here. And X and Y here. So what they're actually doing, they're keeping the front carbon the same, and they're rotating the back one in the Newman projection. And then they're looking at the relationships between the different protons and carbons in that conformation and predicting whether the coupling constant would be large or small. Okay, so for example, these are kind of small and hard to read, but if we looked at the 3-bond proton-proton coupling between H2 and H3, so here's H2 and H3, they're gauche, and so the coupling constant should be small. All right? If you look at the 3-bond coupling between H2 and C4, so let's see here, where are they? Here's C4, and H2 is next to it. These are gauche, and so the coupling constant should be small. And between C1 out here and H3, C1 to H3, these are also gauche, so they should be small. All right? But let's look at after they rotate one. So here, in the next one over here, so H2 and H3 are still gauche, so that means it's small. But H2 and C4, so H2 to C4, now those two are anti. So you should get a large coupling constant. And H3 in the back to C1, those are also anti. So you should get a large coupling constant. Okay, so essentially what they did the syn, they did the anti, and they did 3 different conformations for each of those. And they came up with patterns. Right? And they also did it for the X and the Y groups are either, methyl or OR, or both of them are oxygenated. So essentially they have this matrix of sizes of coupling constants, and if you compare all of these, maybe that's not true. Large, small, 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 large. These two are actually the same. Small. Oh, I think all the rest of them are different. I thought they were all supposed to be different, but those two look like they're the same. But most all of them are different, okay? Here's an even more complicated situation where they have 2 conformations that are in equilibrium with each other. And so for each of these, what they did is they looked at kind of what we already did. So this one, they would have these 2 conformations that were probably on the previous one, and then they said, these are both small in each of those, so it'll remain small. But if this one was small and this one was large, and those 2 are equilibrating, then the size of the coupling constant should be medium. So you're getting an average. So they made this big matrix of all of these sizes of coupling constants, and I guess those are not actually all different either, because this one and this one are the same, but all the other ones are different. Okay. So what they have to do is they have to go in and they have to be able to measure all of those coupling constants, though. And I've never done this experiment either, so this is called this Hetlock, partial Hetlock, they're calling it there. And the Hetlock is, I guess, equal to a half filtered toxy, whatever that means. You can also use, they said, a phase sensitive HMBC. So remember, in the phase sensitive, if you had like a doublet, you'd have one going up and one going down, so it's easier to pick the peaks, and you can measure the coupling constants between those. But what in this Hetlock, here's an example. And what we're looking at is between, here is, you can't really see that, 3' and 4'. So along this bond right here. Okay? So here's a small part of this Hetlock experiment. And so notice that it has proton axes at each side, right? So that's the toxy part, right? It's a homonuclear in that sense. But along, this is F2 and F1. Along F1, we're seeing that this is being split. This is for H4. So this splitting here we're seeing is the one bond coupling. Right? So this is the one bond JCH. So it's essentially going to C13 satellites. Okay? And in the other dimension, in F2, notice that the cross peaks, these peaks, this one and this one, are slightly offset from each other. Dislocated, they called it. And the distance between this peak and this one, this distance here, is the 2-bond carbon C4' to C3' coupling constant. Oh, I already had this over here. Here's the 1 bond C4 to C4'. But yeah, so they'd have to go through and measure all of these. This says you can do it for, this said for 3, this is the 2-bond coupling. I'm not sure if the 3-bond coupling shows up in the same way. But so here's an example also of the type of molecule that they did it on, right? So, you know, it's very complicated and lots of stereochemistry in these chiral centers, and so yeah, I've never done this, but I think it's kind of amazing that you can go in and pick all these out.
Yeah, it is kind of wild.
Yeah. All right, so that's the last for today. So what we've done is we've talked about relative versus absolute, and we've talked about methods to determine relative stereochemistry. All right, so next time we'll talk something about some absolute stereochemistry.